Hi, hi. Okay, last time we learned how to change the representation of a map when you change the bases. So we have a map, lowercase h, as illustrated by this check-in. We have a map, lowercase h, and we have two sets of bases, b and d, and b hat and d hat. And what we want to learn is how do you translate from the basis pair b comma d to the basis pair b hat comma d hat. And of course, we saw that last time, so this is kind of a long calculation. Let's go through it. So let's see here, just to write down what I have. I'm looking at h takes the plane to the plane, and it maps here xy over to x minus 2y and 2x plus 3y. All right, and I'll copy down the two bases just for reference. B is the standard basis on R2, and D is, as always, I try to pick examples that are not too easy and not too hard. If they're too easy, then they sometimes fail to illustrate all the points you want to illustrate. If they're too hard, then you're just hitting yourself with a stick. Why are you doing that? So D is 1, 0, 1, 1. B hat is 1, 1, 1 minus 1 that we've used so often, and d hat is 2, 0, 0, 3. So I'm trying to pick ones that I'll be able to eyeball, but also ones that are not so easy that they fail to illustrate what I want to do. So let's see here. First thing I want to do is represent with respect to b comma d the matrix H. Excuse me, the map H, map lowercase h. So I got to figure out where does the elements of B go under H. And I think if you apply H to 1, 0, you get to 1, 2. And if you apply H to 0, 1, you get to minus 2, 3. Then I have to represent those with respect to D. So the representation with respect to D of 1, 2, and the representation with respect to D of minus 2, 3. Now I picked ones that a person can eyeball, so let's see, 1, 2. So I think in order to get 1, 2, you have to multiply this second vector by 2. And once you multiply the second vector by 2, in order to get a 1 here, you need a minus 1 up here. And likewise, I can eyeball this. If in order to get a 3 on the bottom, I have to multiply the second vector by 3. Once you multiply the second vector by 3, then you have a 3 up there. In order to end up with a total of minus 2, you need minus 5. Okay, so H here, which is the representation with respect to b comma d of lowercase h, is you stuff those into columns, minus 1, 2, and minus 5, 3, in the right order. All right. Next up is the representation with respect to b hat d hat of lowercase h. So same stuff. It's that's what I meant by a long calculation. I got to figure out where the basis elements go. And 1 minus 1. So let's see. 1, 1 goes to 1, 1 goes to 1, 1, so that's minus 1, and 1, 1, so 5. And then 1 minus 1 goes to 1, 2, so that's 1 minus a minus 2, so 3, and 3 minus 1. I'm trying to do too many things at once here. Okay, so now I got to represent with respect to d hat minus 1, 5, and represent with respect to d hat 3 minus 1. So let's see here. D hat is especially easy, so I guess in order to get a minus 1 on top, I need minus 1/2. And then in order to get a 5 on the bottom, I need what, 5/3. And in order to get a 3 on top, I need 3/2. And in order to get a -1 on the bottom, I need minus 1/3. So that h hat, which is the representation with respect to b hat d hat of lowercase h, is stuff these things into columns. -1/2, 5/3, and 3/2, -1/3. Okay. Okay, I'm going to need another piece of paper to do the second half of the problem. So let's see, the second half of the problem. Second half of the problem asks me to do the change of basis calculation. So part B asks for the diagram, and really the diagram is has saved my answer so many times. When I was trying this for my notes, I got confused and wrote the wrong side, but the diagram straightened me out right away. So the spaces are r² in all 4 cases. So the plane in all 4 cases, I've got a basis B and a basis D, a basis B hat and a basis D hat. I've got a map lowercase h and a map lowercase h. Up here I'm representing it with a matrix I call capital H. Down here I'm representing it with a matrix I call capital H hat. And of course what ties the top line together and the bottom line together is the identity maps. In short, h hat is, you've got to go up, over, and down. You can go straight across, that's this, or you can go up, over, and down. And here's the part that a person gets wrong. Up, over, and down, you write the up first. Representation with respect to b hat b of the identity. Then the over is h. Then the down is the representation with respect to d hat of the identity. So the order is so confusing. I can't tell you how many dozens of times, hundreds of times, maybe thousands of times in my life I've gotten the order wrong. The diagram is a big help for aiding your memory in trying to get it right. Okay, so up, over, and down, remembering to get the right order. Darn that order, but anyway, that's the way it goes. Okay, so in order to write down these parts, I have to write down the representation with respect to b hat b of the identity, and I'll do the d hat d and the d hat in just a minute. On the previous piece of paper, I did this calculation in a certain way, so I'm going to do it the same way here, because when a person is first starting, they should do all the calculations in the same way. At some point, you'll start saying to yourself, oh, I got it, I can take the shortcuts. But when you first see it, you should do everyone the same way. So in short, I'm going to do the silly thing here of writing that the map is the identity. So I'm writing the basis elements 1, 1, and 1 minus 1, and I'm applying the map. I know that's silly. But I'm going to do it anyway, because I'm going to do every problem the same way until I say to myself, oh, I got it already. Start taking shortcuts once you're good at it. I got to represent that and that with respect to the represent that and that with respect to the ending basis. Do you remember that the basis B is the standard basis? So the representation with respect to the standard basis of 1, 1, and the representation with respect to the standard basis of 1 minus 1. So I took that and wrote it there, took that and wrote it there, just as I did on the previous piece of paper. And this is E2. Every vector is represented with respect to E2 by itself. So all this stuff, when a person gets good at this, you start saying, I can skip all those steps and go right to the fine. But when you're first learning it, you should do it everyone the same way. And then I'll skip the matrix for just a minute, and I'll do the representation, because I only have so much room on the piece of paper, with respect to what d comma d hat. And again, the diagram has reminded me why it's d hat here and it's b hat b here, because going up you start with the hat, coming down you start without the hat. So representation with respect to d hat, if I don't flub it up, of the identity. And again, I'm going to do the silly thing. I'm going to write down the basis elements from D. Basis elements from D are 1, 0, and 1, 1. I'm going to apply the map. I know that's silly. And then I'm going to represent those with respect to the ending basis, the D hat. Representation with respect to D hat. Okay, and do you remember D hat is this 2, 0, and 2, 0, and 0, 3? So that's 1 half 0 and 1 half 1/3. Okay, and again, I'll write down the matrix in just a second. So writing this right here, down here, I got to remember this stuff from the previous slide. So let's see, what the heck was H hat? What the heck was H hat? H hat was, so H hat was minus 1 half, 3 halves, 5/3, minus 1/3. That was H hat. And the translation formula for translating from H to H hat is write the B hat B over here, write the H here, write the D hat here. And just I'm going to write them in the order that I said them. So the B hat B goes 1, 1, 1 minus 1. The H I got to remember from the previous, it's minus 1, minus 5, 2, 3. Okay? And the H hat goes here. 1 half 0, 1 half 1/3. Okay, so a long calculation, I know parts of it I made longer than perhaps a person who is good at it would zoom through those, but nonetheless, a long calculation, but it shows the translation. You gotta get the order right. That's the part, as a person who flubs things up, I can tell you, that's the thing you'll flub up. Gotta get the order right, and the diagram is a tremendous help in getting the order right. Okay, very good. Okay, right. Okay, so last time we talked about this equation that we're looking at on this slide right here, and the equation and the diagram are closely related. There's the general diagram. Of course, in the example we just saw, we had the plane for the space, but nonetheless, there's the general diagram, and the diagram and the equation say the same thing. They say that you can do the bottom by going up, over, and down. Up, over, and down. Don't forget the order. Okay. So what I have here is a relationship between two matrices, H and H hat. We saw that at the very end of the check-in. We have a relationship between two matrices, H and H hat. They are related by somehow being H is right multiplied and left multiplied by these two matrices. H is right multiplied and also left multiplied by these two matrices. These matrices are special. They're the representation of the identity, so they are non-singular matrices. They're a special kind of matrix. So I have a non-singular matrix here, a non-singular matrix here. And so when we finished last time, the very last thing that we showed is we'll say that two matrices are related by the term for this relation is called matrix equivalent if there's non-singular matrices P and Q, where capital H is right multiplied by Q and left multiplied by P to get H hat. So two matrices are matrix equivalent if they have this relationship, and of course I'm interested in that relationship precisely because we're interested somehow in maps. So we're taking the point of view here, not to the exclusion of all other points of view, but we're taking the point of view that the primary objects are maps, and that the matrices are used to compute things about the maps. And again, that's not that matrices are foolish or we never think about matrices. Indeed, in a few minutes, we're going to think about matrices directly, the sort of combinatorics of matrix multiplication. But nonetheless, we try to take the point of view that matrices are about meaning, maps are about meaning, and so we want to understand meaning. So when two matrices represent the same map, they in some sense mean the same thing. So we want to say, when do two matrices represent the same map? And the answer is when they are related in this way. We want to come to understand this relationship. When do two matrices represent the same maps? When are two matrices related in this way? So we've seen this kind of when are things the same picture before. We will take the universe of all matrices and split it up into parts. These two matrices are related in the way at the top of the slide. These two matrices represent the same map. And over here are matrices that all are related to each other. Over here are matrices that are all related to each other. Over here are matrices that are all related. We split the universe of matrices up into parts. It's an equivalence relation that basically means that the parts don't overlap. So we split the universe of matrices up into parts where the parts that somehow H and H hat are somehow two different names for the same thing. It's as though you took my name, Jim Heffron, and my social security number, which I'm not going to tell you, and you put them together and say they both mean Jim Heffron. It's some dim analogy. So now how do I know, when I'm looking at a matrix, how do I know that it's, that it's related to this other one? So we want to find, in each part, we want to find one matrix that best sort of explains what that part is about. We saw that before. We saw, for example, in Gauss-Jordan reduction, we saw reduced row echelon form somehow best explains its part. Well, we get the same thing here, is that the matrix in each part has a certain form. The matrix that somehow best represents each part has a certain form. So an m by n matrix of rank k is equivalent to this matrix here, where there are k ones down the diagonal, and everything else in the matrix is zeros. So an m by n matrix of rank k, do you remember what rank k means? Do Gauss's method. When you're all done, there are k many non-zero rows. An m by n matrix of rank k is equivalent to one that is all zeros except for k many ones down the diagonal. And we'll call that a block partial identity. You can see that the upper left is a partial identity, and it breaks the matrix up into 4 blocks. The other 3 blocks are all zeros. The upper left is is an identity matrix. It's only part of the matrix, but it's an identity matrix. Okay, now as so often with the theorems, I'm going to do an example rather than the proof, but the example will persuade you about what's going on. So I'm going to recall that the non-singular matrices like P and Q can be factored into elementary reduction matrices, Gauss's steps matrices. So this is the matrix, remember, that takes k row I plus row j. This is the matrix that multiplies row I times k, and this is the matrix that swaps row I and row j. I want you to recall also from the mechanics of matrix multiplication, this is what I was talking about a minute ago. We don't sneer at matrices. We're looking at them here and here, but we try to take maps as primary. But that doesn't mean that matrices are beneath us. So remember again that from the left, matrices operate on rows. For example, here we're taking this is the matrix that takes -4 row 1 plus row 3. If you apply this matrix from the left, it acts on the rows, -4 row 1 plus row 3. And if you take the same matrix and apply it from the right, it acts on the columns. It happens to do -4 times column 3 plus row 1. It acts on the columns. So from the left, matrices operate on rows. From the right, they operate on columns. That's just the mechanics of matrix multiplication. We're going to use those 2 pieces of information here to figure out how to write this matrix into block partial identity form. This matrix has rank 2. If you do Gauss's method, you'll get 2 non-zero rows and of course a 0 row. I'm going to find the P and Q. So, as so often happens in this class, it involves Gauss's method. I took the matrix and applied the Gauss's method steps. See the -4 row 1 plus row 2? minus 4 row 1 plus row 2. Remember, it's got to go on the right. That's because of the order in which these things get multiplied. Minus 7 row 1 plus row 3, there it is. Minus 2 row 2 plus row 3, there it is. Turn the diagonal entries into ones, there it is. When you put those four together, they perform these operations. If you multiply them all together, and it took me a while to get it right, when you multiply them all together, you get this fella here. It just happens to be what you get. So far, the calculation that I have, acting on rows first, is that if you multiply here times the matrix we're interested in, I haven't figured out Q yet. If you multiply here by the matrix we're interested in, you get, it's not quite in block partial identity form. It's got stuff I got to get rid of, but it's starting to look like a lot of zeros, and there's ones on the diagonal. Starting to look like a lot of zeros, and there's ones down the diagonal. So to get the P, you do Gauss's method, arrive at echelon form, do that in matrices, remembering the order, multiply it all together, put it there as P. Okay, what to do next? How to get Q? So you'll remember that multiplying from the right, you act on columns. Multiplying from the right, you act on columns. So I did column operations. To get rid of this 2, we've never done column operations before, but they're not all that different from row operations. To get rid of this 2, I took minus 2 times column 2 and add to column 3. Minus 2 times column 2 and add to column 3. And then when you follow through, you can do that yourself. When you follow through, you take minus 2 times column 1, add to column 2 to get rid of that 2 kind of stuff, and then column 1 plus column 3, and you end up with this. So I use column operations to use this 1 to get rid of that 2, and then to use this 1 to get rid of the stuff to its right. You combine the reduction matrices to get capital Q. You see it over here. The only trick here is that in contrast with the construction of P, they go left to right. Minus 2 column 2 plus column 3 goes to the left. Minus 2 column 1 plus column 2 goes next leftmost. And then column 1 plus column 3 goes next leftmost. Because you see, here's the H right here. So this is the first thing done to H. This is the second thing done to H. This is the third thing done to H. So that's why they go left to right, whereas the matrices in the other half go right to left. So nearest H, next nearest, next nearest. Anyway, you put them down, P, H, Q, you get the block partial identity form. P, H, Q gives you the block partial identity form. It's not a proof, it's only an example, but it's pretty clear that you can do this with I's and J's, isn't it? One reason we're interested in this particular matrix, we think this is an especially handy matrix, is look, it's easy seeing what it does. If you take this matrix and multiply it by xyz, matrix vector multiplication by xyz, it gives you xy0. This is straightforward projection. This projects from R3 down to the xy plane. Now, this is a 3 tall vector, so I didn't say R3 to R2, but nonetheless, this is a straightforward projection down to the xy plane, so it's easy to understand its action. So from among all the matrices that are 3 by 3 and have rank 2, in some sense, this is the one whose action is easiest to understand on a purely mechanical level. So that's why I'm calling it the canonical representative, the somehow best representative of its class. The class is the 3 by 3 matrices of rank 2. So, matrix equivalence classes are characterized by rank. Two same-size matrices are matrix equivalent if and only if they have the same rank. And it basically boils down to they can be put in that form. They can all be put in that form, so they're all interrelated. If you have two 3 by 3 matrices, if you have a pair of 3 by 3 matrices of rank 2, then they're related. Both of them can be brought to this block partial identity form that we were just looking at. So you can, if you have A and B, and they're both 3 by 3 matrices of rank 2, you can bring A to the block partial identity form. You can bring B to the block partial identity form. So you could bring A to B by bringing A to the block partial identity form and then reversing the steps to get to B. So it's a big chunk. Every 3 by 3 matrix of rank 2 is equivalent to the one that we just had on the prior slide. Whoops. Here. Here also. Skip past it. Here also. Okay. So two same size matrices with the same rank are equivalent to the same block partial identity form. Okay, very good. Okay, so that ends the material from change of basis. We've pretty much nailed the problem. We completely understand which maps change to which other maps. And so next time we're going to do something different, going to do something with a little bit of geometry in it, orthogonal projection. So it's got some nice pictures that we can draw. Okay, very good. See you then.